dear colleagues, dear guests, ladies and gentlemen. I'm very happy that we have this first general assembly for the TWENTIES project. Welcome to the assembly and welcome to the city of Copenhagen.
We are leading the seismic wind demonstration. It's the first demonstration of TWENTIES project, focused on providing new ancillary services from wind energy, secondary frequency control with grouping and several wind farms on several clusters, and also to provide voltage control on the 400 kV grid of the Spanish TSO Red Electric as well. The first demonstration, we could be able to balance ourselves by providing this power reserve into the system. More wind energy, instead of curtailing the wind energy, this energy could be used for balancing the system itself. So the first benefit is for the electrical system itself, but lower reserve, lower cost of the system, to ease the life of the TSO, in fact, for balancing the wind energy. And as a society, there will be more green energy into the grid. So this is the grid big effect of this demonstration. And regarding voltage control, the big achievement is as well to as much wind energy is into the grid, as they are not so powerful to control the voltage of a node of the TSO grid. With this service, with this voltage control, the margins, the security margins regarding voltage collapse will be increased again. So more wind energy, not affecting the voltage collapse margin security factors, and obviously a further integration of wind energy. These new tools could be adapted to any existing wind farm worldwide, or at European level and worldwide even. So it's only changing tools, changing algorithms, changing EMS systems, and could be applied to any wind farm already on stream on the European Union. So it will allow to reach the 20% of renewable energy into the system in a better way and in a short time.
And we also believe that we will basically press down the cost of balancing the system by providing more producers of flexibility to the system. So make it cheaper to make this renewable revolution. My name is Anders Birke. I'm demo lead of demo number 2, which is introducing a virtual power plant as an ancillary service provider. So what's the solution to this problem? Basically, it's taking a lot of different decentral energy resources. It could be producing ones or it could be consuming ones. Producing, it could be an emergency genset at a hospital. It could be a small hydropower plant. It could also be consuming, like it could be a cold storage. It could be a skating arena. It could be a foundry. Just units that has some kind of flexibility in the way they can be operated.
My name is Ivan Christian Petersen. I'm representing Dong Energy, and I'm the program manager for the Power Hub project, which is an integral part of Demo 2. Receiver of the services from the VPP will be the transmission system operator, but at the same time, the services that we provide could also be very useful to the distribution system operator, as well as the owner of the assets, which is participating in balancing the system. There'll be an additional need of flexible energy resources that can balance the system, and a virtual power plant can deliver those services. The most important stakeholders will be the players in the vertical industry. Actually, the people who's providing the technology platform for the VPP, as well as the integration components in the far end of the value chain. We'll show how we can control wind farms, that we can ramp up and down, that we can have complete knowledge about how and when wind power is produced, be better at prognosing what's the need of the next hour or the next day, and we will try to deliver the services that is needed to compensate for when the wind is not blowing or when the wind is blowing too much. We basically almost just want to create a power plant. Of course, it will not be delivering baseload, but it should function in the same way.
it should be as reliable as a standard power plant.
If you look at the big challenge for the energy system in the future, looking at the 2020 strategy from the Commission, I think that the 20s will provide some answers, not all answers, but some of the answers to the big question: how are we going to cope with large amounts of renewable energy in the future?
The topics that are dealt within Demo 3. Demo 3 is dealing with the technical and economic feasibility of HVDC offshore grids. The major task here is to properly define the economic criteria that are going to be used to assess the global adequacy of the European power system integrating this offshore wind, and for different topologies of this offshore grid. The second point, which is very important, deals with the technical requirements to make this DC grid, of course, feasible and operational from a power system point of view. That means in normal conditions, but also in disturbed conditions. When you have a short circuit on a cable, what happens and how do you cope with this situation? We try to develop a methodology to design a DC grid and also to deal with all the technical aspects of operating this DC grid in a safe way, let us say, when it's connected to the EC grid. The network's topology and the network's operational requirements will impact on the performances of the DC breaker of the whole DC breaker and functions we can implement on a DC grid in the future. We will develop a DC breaker prototype. Alstom Grid will develop this prototype and provide the test results in the final deliverable. Everything has to operate perfectly together, whatever the manufacturer will be. ABB, Siemens, Alstom Grid, all this has to work perfectly together. The first one was provided in April 2011, and it deals with this preliminary analysis of what is needed for protecting this HVDC network.
The first idea was to think of a DC grid somewhere working like something like an AC grid, where you replace the generators by DC converters, and you will find some DC breakers like you will find in AC. On an AC grid, you have some inertia. When you have a big fault, you will have a loss in the frequency. You will see some quite low, compared to DC grids, quite low variations of the frequency. In a DC grid, when you have a fault, you will have a very big dip and very fast dip collapse of the network. And as you have a lot of power stations in parallel connected to this grid, and you share only one information, the question would be who controls the voltage? This would be the main point.
The biggest challenge we have is to design a robust operating control for this DC grid when it is interconnected to the AC grid, and also, of course, to make a step forward in this DC breaker function to try to eliminate the 40 sections of the DC grid. We try to define this methodology, as I was saying before, and apply it to the North Sea and perhaps also to other European shores. And an important thing is the harmonization with Work Package 16. I don't know who is sitting here for Work Package 16, but obviously there are some common assumptions that have to be harmonized at the beginning, at the very beginning of the simulations.
What we are doing at this moment is, first we have different type of simulations. One with MATLAB Simulink, with average model, in order to look at the different strategy of control and see whether they are stable. And we have also some other simulations which are running with electromagnetic transient programs. Another big challenge is how do you take care of faults? In an AC grid, when you have a fault, you can reach the currents, the fault currents can reach within a few tenths of milliseconds, 40 to 60 and more maybe, kiloamps. But you have zero, and you can stop the current at a zero crossing. In case of a DC, you can reach such high currents, but you will not have a zero. So that's a problem. Maybe somewhere we could, at one time, we will have to go through something like a grid code, I believe, in order to put some rules.
So these are results for TSOs and also for manufacturers who need a clear framework to start developing these devices for the future offshore grid.
I'll be presenting Demo 4, which is the second demo which is going to support Task Force 2, which is the task force that is focusing on allowing more offshore wind power into the system. The countries in the EU or in the NSOE is engaged in having a lot of wind power installed in the future. There will be issues that we need to be solved in order to do this in a safe way. And therefore we need to solve the issues that are related to large-scale offshore wind or large-scale wind implementation in a hurry. And the TWENTIES project will help doing that. What do we do when the storm hits and we have a whole lot of wind power installed in the offshore? So here's the main objective of the demonstration, which is presented in the document of work. It is to demonstrate how to shut down wind farms under stormy conditions without jeopardizing the system. The approach we're going to take here is we are using the Hornsrev 2 offshore wind park, which is about 200 megawatts installed capacity. It's 91 turbines of Siemens type, which is already operating in Hornsrev. And what we are going to do now is that we are going to demonstrate that a wind farm can be regulated according to the TSO or producer before the storm. That gives some requirement to the forecast because it's something that's going to happen before the storm hits. We're also going to look at what we do with the energy deficits, how that will develop through the storm. We're also demonstrating how the energy deficit can be handled with regulating power as part of the system balance, because we are not going to manage one wind farm during one storm on its own. We're going to have an overall system look at this and to have a sort of scene. We were going to see all the wind farms or all the system, how that's going to behave. And that is the jeopardizing the system part of this demonstration. As Demo 2 was also discussing, nothing is going to happen unless there's a market incentive for this. So we are actually going to involve the market to see how the market can help us doing this. It will not give us any additional cost because we can do it throughout the market, and the system also has to be handled today. We have taken a number of events here where we have seen there's a storm, and which one of these can we forecast? And almost all of them is not forecasted because it comes up with a very large forecast error in this. So there's a very big chance that we will not forecast the storms that actually happened, and the ones that we are actually forecasting will not happen. The forecasts are there to give information about the available production from the wind farm. We are using this forecast for us as an TSO is to forecast the system balance. We can actually activate regulating power, which is cheaper than automatic power and so on. Then, based on all this work with partly the forecast and partly the turbine control and so on, it is going to be possible to export some of this imbalance to Norway via the HVDC. It's not going to be interesting to export the balancing of the offshore park on its own, but it's only going to be interesting, or it's for us, it's going to be more interesting to export the system balance or imbalance to Norway, because it is going to be handled via markets where this offshore wind will land in onshore. What we are going to do within the next period now is to have this turbine controller implemented into Hornsrev 2, which is not going to be too far into the future. So I hope that the storms occurring this winter, and I hope a lot of storms will occur,
Hello, I'm Wim Giels from ELIA. I'm responsible within ELIA for the National Control Center. And we are active in the demo 5 Netflex. We are the demo leader, and there in that demo we are trying to prove what we can do about the integration of the renewables, the wind energy and the flexibility in the grid. Because the volatility of the wind farms, the wind energy, pose a lot of challenges for the transmission system operators. So not only in real time, but also in the planning stage, because we have to give, for instance, in the planning stage, the capacities to the market, and we have to be certain that the capacities will be guaranteed. So we have to deal with that kind of volatility, uncertainty about the output of wind farms. And there our demo, Netflex, can give a part of the answer. So we're trying to see how much more wind farms we can connect to the actual system, how much more wind power we can handle in the grid without making huge investments.
The partners in Demo 5, Netflex, we have Alstom and Siemens. We have 3 Belgian universities of Brussels, Louvain and Liège. We have 2 transmission system operators, RTE and ELIA, and Coreso, a regional coordination initiative of RTE and ELIA, and in the meanwhile joined also by the TSOs of Italy, Terna, UK, National Grid, and one of the 4 German TSOs, 50 Hz transmission. So what's the demonstration about? Well, we all know that wind poses some problems. Nowadays we call them challenges. The volatility of the wind, not only in the real time, but also in the planning stage, because we have to determine market capacities. It has also an impact on the reserves, as demonstrated by Demo 1. But also, wind is not always bad for the operation of the grid. When you have more wind, you have more wind production, of course, but you have also a better cooling of the lines. So you could connect more wind farms to the grid, and you could handle more flows through the grid. So that's the aim of the demonstration Netflex, is to see is there more flexibility within the system, but maintaining the same level of security of the grid.
This project gives a lot of opportunities for more connection to wind farms, so we can quicker connect wind farms to the actual grid, so they don't have to wait until investments in the grid or reinforcements in the grid are done. So we can give more connection to wind farms in a quicker way, but also we can guarantee a securer grid, so we can guarantee more capacities to the market. So our customers in that demonstration are producers of wind, but also all the other market players. The biggest challenge in that demonstration is that we are going closer to the limits of the grid. We are operating the grid closer to its limits because we are integrating more wind energy in the grid. So we have to analyze, assess if the security of the grid is maintained, and that's the biggest challenge. So because we are, as a transmission system operator, are always responsible for keeping the lights on, so guaranteeing the security of the grid.
First stream is about dynamic line rating, and there we installed 10 Passimon devices in the ELIA grid to monitor the ampacities through the lines. Not only in real time, but the challenge here is to make a forecast of the ampacity in the future, taking into account the meteo prediction, the wind forecast prediction, so that we can forecast also the future ampacity, the future flow that can go through the line some hours before real time, or even 48 hours before real time. The challenge is that is the low wind speed and the prediction for the low wind speed, and also the wind direction.
It's important for the EU to have this kind of project, this TWENTIES project, and to the different demonstrations in order to show to the outside world that there are solutions, short-term solutions, mid-term solutions, in order to reach the 2020-2020 targets.
The demo 6, or same as the demo 5, is in the task force 3. We try to develop devices and tools with the aim to give more flexibility to our grids, transmission grids, with the aim to integrate all the renewable energies. In this demo, with two different but related developments. The first one, we will try to identify the latent capacity that we have in our infrastructures using the dynamic line rating, and in the second hand, trying to develop a device to manage all these capacity gained with identification in the first step, and try to manage all these power flows. This is the solution that we present in this, that we will develop in this demo. This solution consists in, first of all, we know that when there is a lot of wind, we will have a lot of wind production, of course, and we will have also our infrastructure more cooled, and because of that, we will have an extra capacity in our lines. We propose to identify this extra capacity with RTTR DTS OPPC system. The OPPC have to be similar as possible to the other conductor in this case, and is the most common in Red Eléctrica, is to construct an infrastructure with twin bundle conductors. Because of that, both subconductor have to be have to have the same weight, the same elongation coefficient, because if not, you can have problems about torsions or something like that. In this year, we will manufacture all the OPPC, the other 30 kilometers of the OPPC. We will construct the towers, and we will start with the laying of the OPPC and making the joints of the OPPC also. And right now, we are specifying the algorithms and models that we need to identify, first of all, the capacity, the real capacity of the line, and to make the forecast in 2 hours, minimum 2 hours, with the aim to integrate all these models and algorithms in our EMS system, and to be controlled by our SCADA. With the second part, we propose to specify the specification, the construction, and the installation of a new device to manage these power flows. We are only want to be faster and to give a good solution to this problem, but with this economical point of view also involving the design. We are doing this device with ABB, and this device is the combination of reactor, switch, control by steps. This is the overview of the device. We are using no technology. The reactors, air core reactors, also will be adapted to all the scenarios, because we can change the rate of these reactors. We can put more steps if we need a more accuracy device, more accuracy result. And well, to finish, this is the list of deliverables. You have a public version of all of them, and that's all.
Well, the work package is number 15, and it's one of the 2 work packages within TWENTIES project that have a transversal structure in such a way that they try to learn from the different demos that have taken place, and our main objective is to perform an economic impact analysis and also try to identify which are the barriers that prevent from taking advantage of what the demos have proven to be useful for the whole system. The structure of this Work Package 15 relies on an academic institution like ourselves. We are a university, Comillas University, and all the work is developed at the IIT, which stands for Instituto de Investigación Tecnológica, which is Institute for Technological Research. The questions that we have to answer are very easy to formulate, but there are many different ways in which they can be approached. So it's not a trivial question to perform this kind of analysis. TWENTIES project is a great opportunity here in Europe to put in the same team, in the same group of work, the different agents that normally have worked in an isolated way. Right? Here is a good forum where we have, as I said before, renewable energy companies, manufacturers, academic institutions, vendors, everyone working in the same project. And when you have a unique objective or the same objective, makes easier the communication of all the system operators, renewable energy companies. It's important to have, and in terms of the European Union perspective, if we want to reach the 2020 objectives, this could be, of course, not the only way, but just a step within this ambitious but realistic goal.
My name is Paul Sørensen, and I am employed with the Technical University of Denmark as a professor in DTU. I work on the integration of wind power into the power system with R&D projects. In the TWENTIES project, I am the work package leader of work package 16, and the task of work package 16 is to scale up the findings from the demos, the 6 demos that we are doing in TWENTIES project, to give an idea about what is the impact on a European level of those demos. By the end of the day, we want to answer what is the economic impact and what is the impact on the environment if we are successful with the demonstrations in the TWENTIES project. So what we try to highlight is what difference does the TWENTIES demonstrations actually make to the society in terms of cost of energy, in terms of emissions by 2020. It is very important that we have the TWENTIES project because we are facing very high challenges with the very ambitious targets that we actually have already by 2020 in integration of renewables into the European power system. To handle these power systems that we have no really experience. Of course, we have experience in Denmark with very high penetration, but for a large area like the European, there is no experience anywhere we can turn in the world where we have experience with this high level of renewable energy in the power system. So we need to provide the solutions. We need to demonstrate solutions, and we also need to assess how useful they are in the integration by 2020.
I'm in the work package 17, which is about permits and consents, licensing. It's because of our experience in the process of laying interconnectors in the North Sea. It takes a long time, long lead time to make the permits and the licensing for the interconnectors. And now, especially with the North Sea offshore grid coming in the future, we like to increase the speed and how you can get the permits. The biggest pain point is the barrier, the long lead time, and the public acceptance of interconnectors and wind farms, and also the private parties which have also another interest like fishery or sand recovery, and so we have to manage the different interests in the North Sea. The EU wants to have more wind integration into the electricity system, and if it's a technical solution, then you need it also in the organizations of the companies. And we hope that we can speed up the process of the permit so that the European Commission can realize the infrastructure and as soon as possible.